Hello everyone. So we are in chapter 2 and chapter 3 this week. This is beginning of week 2 of this course. In chapter 2 we're going to look at 3 sections. Section 2.1 probability, definition of probability, and looking at approaches on finding probabilities. In section 2.4 we're going to look at random variables. We looked at variables last week, so this is a continuation of that work. The difference is the word random. And that means we don't know the value of the random variable, basically. That's why it's random, because we don't know the outcomes. In section 2.5, we're going to take a look very briefly at continuous distribution, what it is. We're not going to do really much in that section. And then we move on to section 3. Now, we have a lot of stuff, a lot of ground to cover in this week, and we're going to spend a good portion of our time looking at Minitab. So everything that is in this lecture in this week, we will actually use Minitab, and I'll show you step by step, click by click, how to actually perform what we're doing. All the examples that you will see that I have done, we'll walk through and actually do them in Minitab. So the lecture actually is going to be quite long. I'm just guesstimating it may be about hour and a half, maybe hour 45 minutes. So you might want to pause the video and then just go out or just get out for a few moments to stretch and what have you, so you don't get too bored with this. Otherwise, it's going to be a lengthy lecture. So let's actually begin in section 2.1. In section 2.1, we're going to define probability. Now, here's my one-sentence definition of probability. I'm sure we all heard about probability before. We even make our own probability statements, hear about probabilities all the time. And so this is one way to define probability. We're going to call probability the likelihood of occurrence or non-occurrence of an event. And that's all that is. The likelihood, that means probability for us. So if I defined event E to be just that, probability of that event is what P of E represents. Now, being probability, that means the probability for any event lies between 0 and 1 inclusive. So we cannot have negative numbers for probabilities, and we cannot have numbers greater than 1. And of course, we can write probabilities as fractions, we can write them as decimals, or we can write them as percents. So when we say 1, that means 100%. If an event E has probability of 0, we call that an impossible or an improbable event. And if the probability of that event E, a different event, is 1, we call that a sure event. Now, how are we going to actually assess probabilities? There are 3 approaches to probabilities. So, first of these 3, that's the subjective approach. With subjective approach, it's just that. The results, the numbers that you hear, you work with, these are subjective guesses. So they're not objective. So usually these are based on some kind of a personal opinion, based on judges, panel of experts. Sometimes we have some collateral information, so things like that. There's really no concrete work behind it. Again, there's no objectivity in this assessment of probability. So for example, what is the probability that something breaks down in a computer, under the hood of a car? These things are pretty subjective. If you ask a mechanic what is the probability of getting a flat tire, you may hear a different number from different mechanics. Okay, so here I have an example of what would be a subjective probability. For instance, I want to know, well, what is the probability that the Fed will hike the Fed fund rates during the next FOMC meeting? Well, personally, I have no idea what that probability is because I'm not an economist. But this would be a good example of subjective probability, because maybe I know an economist, maybe I have a colleague who's an economist, and I can ask him, and he or she, if I ask him or her, I should say, then I get different numbers. Somebody may say, for sure, they're not going to raise the rents because of the current environment we are in. So that would be a sure event, 100%. That's just a subjective opinion. Another economist may assess that same phenomenon with a different probability, maybe a higher probability than 50%. And another economist may say, well, it's going to be about 75, 80%. So you kind of get an idea about this. These are not objective assessments. They're just subjective. So we will not be using this approach going forward in this course. We would like our probabilities to be objective so that we are all kind of get the same numbers more or less. So each of us is not going to have a different number, our own probabilities. So with that, we go to our second approach to probability, namely the classical definition. So here I have bulleted these classical definition of probability. And this is an objective approach, so it's not subjective. And the bullets are very important. These are the highlights of what we call the classical definition. So first, foremost is that we need not to conduct the experiment. So this is a big plus for classical approach to probability. I don't have to actually go out in the field, and I don't have to collect any data in order to assess the probabilities. Usually we use classical approach for problems that are well defined and they could be modeled mathematically. And in this approach to probability, the assumption is that we have equally likely outcomes. Okay, and don't worry about these technical terms or jargons. What is an experiment? What is an outcome? Things like that. Going down further in a few minutes, I will actually give you all of the definitions of what do we mean by a trial, what is the data, what is outcome, what is sample space, things like that are coming up. So the assumption here is that we have equally likely outcomes. Outcomes must be independent. That is a statistical independence we're talking about. So pretty much, but what we mean by idea of independence is that what happens, the result of an experiment, let's say. When outcomes are independent means there is no correlation between occurrence or non-occurrence of these outcomes. So just because something has happened, it doesn't mean it's going to influence or affect the probability of something else happening. So in that sense, the outcomes are independent. And this models probability mathematically. The classical approach does. And this is important. If we can model things, then we get exact probabilities. And by exact meaning, it is just that. It is not based on a sample. So I'll be able to clarify this idea of exact probability in a few minutes when we look at the next approach. So having said all that, how do I find probability? Simple. Probability of any event E is equal to little f over cap n, where little f here, the numerator of this fraction, is the number of outcomes that are favorable to event E, whatever that event might be. And the number in the denominator is going to be the total number of outcomes in sample space. Okay, so that ratio pretty much gives me the probability of an event. So to give you an example, for instance, let's say in the game of poker, okay, where you're dealt a 5-card hand from a standard deck of cards with 52 cards. There are 4 suits, 13 denominations, right, 52 total. So for example, let's say I want to know what is the probability of a full house. Okay, well, to find probability of full house, the denominator, I need to be able to count how many 5-card hands can I be dealt. So that's going to be the total number of outcomes. Okay, all possible 5-card hands that I could be dealt. And then the numerator favorable outcomes here would be all different possible ways that I could actually be handed a full house. Remember, full house, for those who don't play it, a full house is when you have 3 of 1, let's see, it's the same denomination, right? For example, we have 3 5s and 2 kings. So you have 3 of 1, let's say it could be any numbers, 1 through 10, and then you have your face cards, Jack, Queen, King. So that's what a full house would be. 3 of same, let's say, denominations, and 2 again different but same denominations. But anyhow, the idea is that if I want to find probability of an event such as that, then I need to be able to count how many ways I can actually do something. Okay, so that's what that is. Now, again, going forward, the reason I'm not spending too much time on this is because going forward, we're not going to be doing probabilities using these methods. We actually use the next approach, which is based on data. So our next approach to probability is the relative frequency concept of probability. And here are, again, the bullets. These are the signature, I call it, the signature of the relative frequency approach to probability. So it's kind of like part of it is the same as the classical approach, but in other ways it's different. So for example, the fact that the outcomes are equally likely, that was the same as the classical definition. And by the way, the relative frequency approach is also an objective approach. It is not subjective. And for this one, unlike, in contrast to classical definition, you actually have to conduct the experiment. Okay, we must conduct the experiment. Even if I could model it mathematically, I have to conduct the experiment. So for example, let's say we know the probability of a head or a tail when you toss a fair coin is 50-50. Well, there you go. That was just classical definition, right? Now, if I want to assess that probability of a head or a tail with relative frequency, I actually have to toss the coin. So maybe I toss it, I flip the coin 100 times, and I look at the ratio of times that I have actually observed a tail. And that will give me a probability of tail. Okay. Now, because we must conduct the experiment, then these probabilities are experimental in that they depend on how many times we conduct the experiments. So, third bullet here, by the way, the trials are independent. When we use relative frequency, we assume trials are independent. A trial for us, by the way, is a repetition of an experiment. So if I toss a coin 5 times, then there is 5 trials of that experiment. The experiment is the toss of a fair coin. Now, trials are identical. Remember, because we have to conduct the experiment, we have to conduct it exactly in the same manner. So, for example, let's say I'm weighing a package of meat at the grocery store. Okay, so if I'm using a digital scale to weigh the packages, I must use the same digital scale as I weigh each of these packages. So I cannot, let's say, change my device, that digital scale, in the middle of the experiments. I cannot switch scales. Then the trials are no longer done identically. Okay. Now, these probabilities, again, are also known as experimental probabilities. The reason, because you conduct the experiment, and as such, they are not exact. They're only approximations. And like I mentioned, if I want to know what is probability of a tail in a flip of a fair coin, well, if I conduct this experiment 100 times, I may get 40 out of 100, 40 tails out of 100 flip of a fair coin. So as of the 100th trial, the probability of a tail for me would be 40%. Now, if I conduct the experiment 1,000 times, I might get 520 tails in 1,000 trials. At that point, the probability of a tail becomes 52%. So you see how the probabilities actually change depending on how many times we conduct the trials. So in that sense, they're approximation and they're not exact. Unlike the classical definition, remember in classical definition, because you do not conduct the experiment, it's based on a mathematical model. The probability of a tail or a head is exactly 50%. So that's what we mean by exact, because they are independent of the experiments, because the experiments are not being conducted. So how do we assess probability now? Well, the probability is this time, notice I'm not using equal sign, I'm using this approximation sign. The probability of event E is approximately equal to the frequency of times we observe event E over the number of trials. That's what N is here, the number of trials. So we just take a ratio of those, or a proportion, a percentage of times event E is observed or occurs in a large number of replications. Again, N is a number of trials. Replication of the experiment is a trial. Now, how is this going to help us? How is this going to actually validate the probabilities then, if it's going to be approximate? Well, things in theory work out nicely, right? But in practice, it's a different thing. So what actually validates this approach to probability is the law of large numbers. Now, there are different versions of the law of large numbers. The law of large numbers we're going to look at in a moment is going to tell us that if we conduct the experiment a large number of times, you just keep repeating the experiment over and over and over, then the probability of event E will actually approach the exact probability. Okay, so I have the law of large number as the backbone. It's the theory behind the relative frequency approach. But in practice, by the way, folks, we don't really practice law of large numbers, because let's say I go take a sample of 100 new businesses that have been in business for 2 years. And I want to know what percentage of those are going out of business. Okay, well, I'm not going to conduct this experiment over and over and over. I can only afford to survey 100 businesses that have been open for the past 2 years. Okay, and look at, let's say, the records of businesses that have been open for 2 years, and look at how many of those have gone out of business. So again, this law of large numbers is what I call the pie in the sky for the relative frequency approach. Now, here's what the law of large numbers says. As you repeat the experiment over and over, the percentage of, or the proportion of that ratio of F to N approaches the true probability of event E. The true probability is what nobody knows when we conduct the experiment, by the way. And here I have a couple of graphs. Let me enlarge them for you. And there you go. Now, what are these two graphs? Well, these are computer simulation, toss in a balanced coin, a fair coin, 100 times. So look at, you get two different actually charts. These are two different graphs because they're based on experiment. So initially, something that's interesting, initially means I'm looking at right in here and look at right in here. You see, initially those zigzags look different. That's because the number of trials are not that many. So it really makes a difference whether you observe a tail or a head. Okay. And in this experiment, we're looking at the number of heads here, right? Or the percentage of heads. That would give us the probability of head. Now, the true theoretical probability is 50%. We know that, right? So initially, the numbers will be different. And notice how the probabilities fluctuate. So chances are, if you don't conduct the experiment long enough, you don't have the correct probabilities. But something interesting happens to both of these now. If you look at the tail, the right tail of this, let's see how both of these charts are actually approaching 50%, which is the true probability, 50 for 50. So again, initially, that's why when we do our trials, different researchers, they get different results in the beginning, but if the sample size increases, then we all get reasonable, valid results of the experiment. So that's what the law of large numbers says again. And the fact that as the number of trials, number of tosses here increase in both cases, we approach, again, the exact probability in the long run. Okay. So hopefully that's clear. I was able to explain what these are. Alrighty. And done with this. Let me shrink this back a little bit. So here is a list of definitions that I've used throughout the lecture so far. So you can see what these definitions are: precise, concise, but precise. So when we talk about data, we're talking about measurements on a variable. What is an experiment? An experiment is any activity for us that generates or creates data. A trial would be a repetition of an experiment. The outcome of an experiment, the outcome is a particular result. So for example, when you roll a die, you may observe a 6. So a particular result of that experiment would be to observe a 6, to observe a 5, what have you. These are outcomes. Now, events are determined in context of the experiment. These events are usually defined by the person who conducts the experiment, and it's a collection of outcomes. So for example, let's say in a roll of a die, I may define my event to be this. My event is to observe an even digit. See, I define that. Somebody else may say, well, I want my event to be what about observing a number less than 4? So usually the researcher, the experimenter, define these events and then find probability of events. Now, if there is a single outcome in the event, we call that a simple event. And if there are 2 or more outcomes, we call these compound events. A sample space for us, this is like the universe, the totality of all possible measurements. It really resembles the definition of a population that we had last week. Remember, population was collection of all possible outcomes. Well, that's what a sample space is also. It's all possible outcomes of an experiment. Okay, so hopefully those are clear definitions. And we are done with that section 2.1. Now in section 2.4, let's talk about the random variables. Again, last week we talked about the variables. Today we're just going to add the word random to it. Okay. So what is a random variable? Well, a random variable is simply a variable whose outcome, whose values are determined by chance. So how do we label these random variables? We usually use the latter part of the alphabets, X, Y, Z, to indicate these random variables. So for example, random variable X might be the amount of chicken that is consumed by a family of size 4 per year, if they actually are not vegetarian or vegan. So whatever that random variable X or Y or Z might be. Another random variable might be, for example, the PE ratio for the companies that are in a certain industry. Okay, these publicly traded companies. So that's what that is, a random variable. Now there are two types of random variables, just as we had two types of variables, discrete and continuous. Remember again, last week we defined both of these. Discrete are those that have gaps between numbers. Usually discrete numbers, discrete variables are those whose outcomes are counts. Okay, with continuous, usually the values are measured. Like for example, a person's height, weight, distance you travel, things like that. Okay. Now, that's what I just said, or I've written down here. Note that we defined these in week 1. So if you want to review, you're welcome to look at week 1 lecture. So now let's talk about probability distribution of discrete. In section 2.4, we're looking at discrete random variables. And in chapter 3, we actually look at a continuous random variable. So now the probability distribution of discrete random variable, this is going to be simply a listing, like a table of the outcomes or values of that random variable, call it X, along with the corresponding probabilities. That's all that is. It's a simple table. Usually have 2 rows or 2 columns. In this case, I have 2 rows. Now, here I have made up something here. Let's say these are the number of accidents that could occur on a given, let's say, Friday commute on a certain stretch of the highway or freeway. So I have the number of accidents. 0, 50%, there's no accident. 40%, there's probability of 1 accident. And there's 10% probability of 2 accidents. And suppose those are the only probable outcomes. Now notice that these are discrete values because these are counts, right? 0, 1, 2. Now, for this to be a valid probability distribution, by the way, 2 things must happen. The 2 things that must happen are right over here. First, individual probabilities that you're looking at for each outcome, these must lie between 0 and 1. Okay, and they do. So when I made this up, I made sure I made numbers that are between 0 and 1. So you cannot have negative numbers for probabilities or numbers that are greater than 1. And the total of these probabilities should add up to 1. Otherwise, we don't have a complete table. So those 2 things must be in place. Otherwise, this is a valid probability distribution. So what are we interested in this work? When we have, what good is this distribution for? So here I have 4 things that we are interested in when we look at a probability distribution. 1, we may be interested in the shape of the histogram of the distribution. The histogram shows how the values are distributed, and it shows the distribution of probabilities across the values or the outcomes. And then we may be interested in making up some events and find their probabilities, which I'll do in a minute. And the other 2 things that we are interested in any probability distribution are usually the mean or the average of random variable X and the standard deviation of random variable X. Okay, so those are the 2 things you're interested in. Now, for the above probability distribution, in fact, we're going to do all 4 bullets here. Okay, so first of all, here's something that probability distribution is good for. Remember, we can make events and find the probabilities. So I made up some events. So for example, what is probability on a given Friday commute? There will be exactly 2 accidents. Well, according to this data, is 10%. Oh, where do these probabilities, by the way, come from? They could come from historical data. They could come from a function. Actually, we'll see example of functions, probability functions that are capable of generating probabilities. Or they could come from historical data, or they could come from some kind of resources from some database, whatever they may come from. So, probability of exactly 2, let's say accidents, 10%. Probability, and here are the probabilities we're going to find. Exactly 2, and I replicated the table here. So because I'm scrolling, I'm going to lose those numbers that were up there. Probability of exactly 2, that's 10%. Probability between 0 to 2. Now notice, by the way, it's inclusive of 2, means x could be 2. I could have 2 accidents, but more than 0. More than 0. So 0 is not included this time. So the probability of between 0 to 2 exclusive of 0 inclusive of 2 is going to be what? That means probability between 1 and 2 actually, right? Bigger than 0 means 1 or 2. 2 is included, 0 is not. So what I did is I added probability of 1 or 2, and that gives me 50%. Again, note, if I had included the 2 in there, I would have gotten a different probability, and that's this one right up here. We'll see that. So eventually, I'm going to have a case where I have 2 equal signs on both ends, but what I'm doing initially is I'm removing equality from 0. Next, I'm going to remove equality from 2, because I want you to see that whether you include an outcome or not, it changes the probability. So probability between 0 and 2, this time inclusive of 0, exclusive of 2, so that means probability of 0 or 1. That's 50% and 40%, 90%. Look how different these are. And finally, look at the last one. Probability between 0 or 2. Inclusive, that means 0, 1, or 2. Well, that's the entire sample space, all that could happen. 50, 41, that's a sure event. In other words, for sure, you would expect to see either no accidents, 1 or 2 accidents. And there you have it. Now, and I have kind of summarized that in here. It really makes a difference whether you include or exclude the equality in your probability statements for the discrete random variable. So that's one thing we wanted to do. Remember those 4 bullets. The next thing I want to do is I want to look at the histogram of this. So, and this is a probability histogram. I actually used Minitab to do this. And I will show you how to do this on Minitab. Again, in a few minutes, we're going to spend a good portion of this lecture on Minitab. I would guess that we'll probably spend about an hour on Minitab in this lecture. Okay, so this is what the probability distribution looks like, the histogram. You have each bar represents the value of random variable x. This is 0, 1, 2. Now, personally, honestly, folks, I don't like the way Minitab shows this histogram as a connected bars, because you can see 0 to 0.5 here, 0.5 to 1.5, 1.5 to 2.5. To me, it gives the impression of continuity. And remember, these are discrete random variables. There is no continuity between the scores, right? You have gaps between numbers, but these bars tend to hide or mask those gaps. Some other software actually, they use spikes. They use a tiny line that actually erects from 0, 1, 2. So this is what I mean. Let me show you an example of what I mean here. I'm going to actually insert a shape here. Let's see. Let me use my pen. Okay, and I show you what I mean by spikes. Okay. So, for the shapes, it's not cooperating with me. That's okay. Okay, now it's doing it. Sometimes my notebook hangs up, that's why. So, this is what I mean by spike. There you go. This is what it's going to be used right there. Okay. And another spike would be at 1, and it starts from 1 and it goes up to the bar, and the other spike is going to occur at 2. So this is how some softwares actually do this. You see that? To me, that's much better than showing bars. But anyway, nevertheless, that is what that is. And I can see why Minitab does it. They want to give the idea or an impression of the general shape. Now, by the way, in a histogram, typically what we like to do is we would like to see trends. So for example, and for this data, here's the trend that we can see. We can see that this thing is going down, right? So it looks like the distribution of probabilities is skewed to the right. So let me just summarize these. These are the kind of things we look for in a histogram. If you smooth over the bars, we're looking for skewness, whether it is to the right. This is an example of a right skewed histogram. Okay, this one. We look for skewness in the other direction. So there you go. This one would be an example of a left skewed histogram. And of course, we can always look for symmetry, and that's what this one is, such as that. This one would be symmetrical. Now, it could be symmetrical like a U shape, right? It could be symmetrical in a triangular shape. It doesn't have to be like this bell-shaped distribution. But typically, generally, this is what we look for in histograms. Okay, the shape gives us the impression of the skewness or symmetry of the random variable. Now, the other thing that I had up here in our bullets, so we looked at histogram, we look at making up events, finding probabilities. Now we're going to look at the mean and deviation. So how are we going to actually do mean and deviations? And I haven't forgotten. I know I have to show this probability distribution using Minitab. We'll do that in a few minutes. Okay, so let's actually now take a look at the mean here. Okay, so the mean of the random variable, that's mu of x. Okay, sorry about that. The mean of this random variable is mu of x, which is equal to E for expectation. It's also called the expected value of the random variable x. Now, we are assuming, by the way, that these are theoretical distributions for the random variable x. That's why we're using population parameters mu and sigma. Okay. So how do we find the mean? Here's our formula. Sigma x times px. And I'll show you how this formula works in a moment. One thing we don't do is we don't do straight average. So I'm not going to do, for example, x's were 0, 1, 2. You're not going to do 0 plus 1 plus 2 divided by 3. It's not your ordinary average. So this means you multiply the outcome times probability of the outcome for the random variable. The variance has this formula. And again, I'll show you in a moment how this actually works with our made-up example. So for the variance, you're going to do x minus the mean. So it requires that you find the mean first before you can do the variance. So we have x minus mu. You square that and then multiply it by probability of x. And that's how we're going to do this one. Now this quantity, by the way, x minus mu, let me write that for you, x minus mu. This is called a deviation. A deviation from the mean. That's what that is. It's deviation of a single score from the overall mean of the let's say data. It could be the mean of the population or mean of the sample later on. And that's what that is. And when you square it, it becomes a mean squared deviation. And of course, for this one, we're multiplying it, we're going to multiply times it by probability of x. Okay. Now, let's do that actually for our made-up example. I want to find the mean and deviation. So first, the mean. Remember, xpx. So I'm going to multiply the outcome. That's 0. That's x. Px is probability of that outcome. So I have 0 times 0.5. Next outcome, probability of outcome. That's the next one. Plus outcome times probability of outcome. And the reason we are adding them is because of that sigma. The sigma in front, that's a command to add. That means add them up. So you work the arithmetic. I got 0.6. And we'll verify these numbers, by the way, in Minitab in a few minutes. How do I calculate the variance? Well, once you calculate the mean, now I can do this sigma. So again, you do outcome minus the mean of the distribution. Square that, so you have a square deviation, and then you multiply that times probability of that outcome. Okay? And that's what I've done. I multiply 0 minus 0.6, so I created the deviation from the mean. That's the deviation of 0 from the mean. Negative 0.6 means it's 0.6 units below it. And then you square it times probability. You do that for the next one and the next one. And of course, you do the arithmetic of this, right? 0.6, negative 0.6 squared. That's 0.36 times 0.5, you get 0.18, and so on. So the sample, the variance turns out to be 0.44. And if you want the standard deviation is going to be square root of the variance. And that's going to be 0.66. So these formulas we need to know. And now we do. Now square root of that gives me 0.66. Now the reason, by the way, we use standard deviation rather than variance is this. With variances, because you're squaring the units, so the units on this 0.44 would be squared. Now, to put it in context of our made-up example, what does mu tell me? 0.6. That means on average, I would expect to see 0.6 accidents on a given Friday. Okay, that's what that literally is. So this would be 0.6. This is actually a count. Accidents per Friday. Now, how can I have 0.6 of an accident true? Which we can't. So we can actually turn this into a whole number. If I think of it this way, this is 6/10, right? 0.6. If I multiply the top and the bottom by 10, let me see. Actually, let me do it differently. So, sorry, let me not do it that way. This is not cooperating again. It's freezing over. But that's okay. So 0.6 accidents per Friday. And that means I can actually do the following for this. 0.6 accidents per Friday. That means every 10 Fridays, right? Every 10 Fridays, we're going to have 6 accidents. So that's how we can actually get around that 0.6. We can turn it into a whole number. Okay. Now, this number 0.44, by the way, the 0.44, this one is in squared units. So what does this mean? This means accidents per Friday squared. Okay, which really doesn't make sense, does it? Accidents per Friday squared. So it is for that reason that we take the square root of this number. So the square root of that number is 0.66. This is back to the original units, accidents per Friday. Okay, and that's what that is. And these are all now Friday. My pen is working. Now, what does again 0.66 mean? That if I round out to 1, that means on average you would expect 0.6 accidents, give or take 1. The standard deviation, this is the interpretation of this at this point, is give or take of the mean. Now remember, if I multiply this 0.6 by 10, 0.6, multiply it times it by 10, it becomes 6, right? Instead of 0.6 accidents per 1 Friday, this would be in 10 Fridays. So you would expect 6 accidents every 10 Fridays. Now standard deviation 0.66, call that 0.7, approximately equal to 0.7. So that means you expect 7, give or take. So the average is, remember, 6 accidents every 10 Fridays. Give or take 7 accidents every 10 Fridays. So that's how we interpret those numbers. Okay. Now, here you go. Finally, we reached this point. How do I do this in Minitab, right? So get ready, folks. We're going to go to Minitab. So actually, what you might want to do at this point, this would be a good break point for you also. I'm sure you're already tired of this, perhaps, since we're going to go to Minitab. So if you would, just pause or stop this lecture, the video at this point, and go ahead and invoke Minitab. Hopefully you've downloaded Minitab 19, and this way you can kind of follow through with what I'm doing. Okay. Now in Minitab, by the way, look, isn't that cool? This is what we're about to get. Now here I actually have something labeled for you. I was messing around with this. I know these two are redundant, so it's not necessary to do this twice. I just want to show you can label these however you want. Just call it deviation, deviation of x, and here's variance, and here's the mean of x. This is actually the 2 columns I actually put in, and the rest of them I calculated it. Okay, I'll show you exactly how these are done in just a moment. Now, in fact, we're going to go to Minitab now. Okay, so let me do that again. Feel free to pause the video at this point and then invoke your Minitab. And I'm going to actually continue on in Minitab now. So here's in Minitab. I'm now in Minitab. Now, this different areas of Minitab, this lower portion of it looks kind of like Excel spreadsheet, right? In fact, it is a spreadsheet. So here we have columns and we have rows. The columns for us are going to be the variables. The rows are going to be observations or the record on these variables. So for example, record number 1, that could be my record, column 1. That would be, let's say, my name, my phone number, my home address, my height, my weight, things like that. It could be any characteristic, whatever the variables are. Remember, the variables are columns. The records or observations are rows. Now in here you have this navigator. Okay, so there you go. As we invoke these procedures, as we run things in Minitab, you're going to see this navigator is going to be populating itself. Everything that you do is kept track of. Your outputs are kept track in the navigator, and you can recall and watch them, view them, whatever. Up here that says Minitab. So, and you can see self-explanatory. You can open a saved file. You can save your files right in here. Just your typical a layout format of file structures in other applications like Word, Acrobat, so on and so forth. So you can pretty much follow these. You can edit in here. If you do something wrong, by the way, accidentally you delete a column of your data or just mess something up, don't be afraid. Just do your Control-Z and it will undo, by the way. This is going to come in handy sometimes. Okay, now up here, let me actually pull down this spreadsheet part. If you want to have a more view of the output, every time you run something, a procedure, the output is going to go up here. So as you just saw me do that, you can grab this thing, move up and down to adjust your viewable area for the output. Okay, and then here, these are the toolbar here, edit, data, a whole bunch of stuff. See all the things you can do. Now, by the way, folks, don't worry. We're not going to look at all the functionalities of Minitab. I mean, that could take a few months just to go over Minitab commands in detail. So we just want to grab and do what we want that's tailored to the course, to what we want to do. Okay. And this is calc, as in calculator. This is statistics and graphs. You have your view tab, your help. I'm sure some of you may need that. I'm gonna need that myself. And then the assistant here, actually, that can give you assistant in any of these items that you may need help with. Okay. Now, let's actually do what we did. We're going to create that probability distribution. Okay. So I'm going to actually type in capital X, right? That was the random variable X. Next to that, I'm going to type probability of X equal little x. This is like probability notation. Or if you want, you can just type probability of X. How's that? So it's not so cryptic. Okay, so I have probability of X and X. Now, these you have to actually input. You could actually import, by the way, your data into Minitab if you have it in Excel or what have you. See in here, data. Should give you, let me see, file. You can open a file, right? And you can data. Let me see here. Anyway, you could, it's in one of these in here, not the edit, but it's either data or file. If you open the file, like an Excel file, there it is. As I'm holding this, the mouse, it reads open a Minitab project. There you go. Open a Minitab project, an Excel spreadsheet, or a text file. That's how you import your data into Minitab if you have it. Like for your project, for example, when you collect data, you can save it in Excel and open it in Minitab to analyze it. So there you go. Here are the two columns, right? Now I'm going to type the values. Remember, the values of a random variable X were 0, 1, 2. Okay, and the probabilities were 0.5, 0.4, and 0.1. Okay, so those are the only things I had. Everything else was calculated in that display. Let me show you again in this one. See, the first two columns is what I input. The rest of these are calculated. So that's what we're going to do next. So first, let's say we want to, at this point, let's say I just want to look at the probability distribution. Okay. So I want to see what this distribution looks like. So I can go to graph. Okay, and then if you go to probability distribution, plot here. Okay, and click on that. And you can go view single right in here, view single. Okay, and let's see. For distribution, we're gonna go up here. See, these are the list of discrete and continuous probability distribution. These are all the well-known distributions. I'm just gonna click on discrete. That's what we're doing, our custom-made discrete distribution. Now, the values are in, see if I click in here, let me backspace and erase these. They're already in there. There you go. So yours should be blank, right? But once you click in the value, you may have to double click or just left click. Values in. Well, the values are in column 1. So double click. The probabilities are in here, so I can go double click or just go probability and select, however you do it. You see that? Let me backspace, double click, it imports it into that field. Now it knows, Minitab knows where the values are in and where the probabilities are, and hit OK. And there you go. And this is the distribution plot. So notice by the navigator here, our first output is saved in here. And if you want, I can shrink this, and this is the view of this probability histogram for this data. You see that? Now, in here, by the way, if you click over here, it gives you options. You can send this graph to Word, you can send it to a PowerPoint, or send it to Companion. That's actually Minitab Companion. It's not like you send it to a friend or a companion. That's not what that is. Or you can copy graph. That's what I did when I put it in my notebook. If you left click on copy, there you go. It's copied now. And then you can right click and copy it into the document that you want to copy it. Okay, so that's what that is. And then of course other options, you can edit the graph. Now if I edit the graph, I'm going to hit edit, and look what happens here. There you go. Now you get a whole bunch of things you can do. You can try these out on your own. So in here, if you hold the mouse on it, it shows you what each of these will do. So for example, you can draw an arrow, and that's what I did. There you go. Here's an arrow. I can add a text in here, and I can write my text. You can just say lowest bar. There you go. So whatever descriptive you want to do. And you can of course move the text around. You can change the font, and in here, if you want, you can draw an ellipse. I don't know why you want to do that. There you go. You can draw an ellipse, and then you can right click. If you right click, something will happen. I don't need that actually now, so there you go. Let me select it and hit delete button. So anyway, you can try this out and see what it'll do for you. Add an item. You can add grid lines, and let's say for X major, X minor, and there you go. You see all these grid lines that are inserted along for the X values. If you want, you can actually go grid lines. I'm going to remove the X's. Usually we see grid lines on the horizontal vertical axis, I mean, going in a horizontal direction, and there you go. That's what these are going to aid readability. So I can see, okay, well, this bar is at 0.4. And notice, by the way, as you move over these bars, like left click once, and it tells you description of that bar. It says X is 1, probability of X equals 0.4. So just explore as much of this as you can on your own time. Now something in here you can actually edit. In here you can change the graph size, custom or automatic. So you can change the attributes of the graph. I'm going to click OK. The other thing you can do here is, let's see, that's okay. Right in here you can, actually let me go to add an item. I'm going to add a title. There you go, title. I'm just going to call it, for example, this is the probability distribution for number of accidents. Okay, and hit OK, and it's right up here, probability distribution of number of accidents. Okay, and by the way, here is the subtitle. If you don't want the subtitle, that's there right in here. You can actually click on these and change the font, change the size, the style, if you want to boldface it, and if you want to rename it. If you want to just delete it, there you go, you can also delete it and hit OK, and that subtitle was gone. The distribution plot, let's see, you can go to title. Actually, I already did that one. Oh, there you go. I just clicked. Let me show you. I left click on distribution plot and see it's selected. Double click on it and you can backspace. Okay, and that's gone. So this is more custom. What else you can do? You can actually add footnotes. There you go, a footnote. I'm just gonna put footnote in class or not on. My keyboard is a little small here, so occasionally I have typos. In class demo. Okay, and hit OK. And right down here, you see down here, that's my footnote. If you don't want it, double click it, delete it. Okay, and it's gone. So you can play around with these tools. This is not necessary. You can just get the basic functionality, but a lot of these you can explore on your own. Okay, so I'll leave that up to you. Question is, how do I get this? And this is how you get it actually. Okay, so that's what I have for now. And that was the histogram. Okay, now let's see what else I want to show you here. If I go under graph, let me go, let's see, graph, and let me go probability distribution plot, and this isn't what I want to do. Never mind, and that's okay. So let's actually complete that table. Now in here, because remember we're going to calculate the mean. The mean was xpx. So actually we need to create a column that multiplies x by px, right? So to do that, we're going to go to this is what I want to do. I want to go to calc, just to show you something. If you go to calc and you go to probability distributions, again, here you see a whole distinguished list of well-known probability distributions. I'm going to go to discrete here, right in here. And again, when you go in first in Minitab, these should be empty, right? Okay, so this is what it should look like. Now, I'm going to choose probability here. Okay, choose probability. And where are the values? They're in X, so select it. Where are the probabilities? Double click, select it. And my input column, I'm going to choose it to be X again. Okay, and look what happens here. When I hit OK, it gives me actually the output nicely. Look at this. This is what I was typing in the beginning, and I said, oh, let me not do that, it's too cryptic. So this actually gives you the probability distribution for your data. And that's what it does. So you don't have to copy and paste it. Now you can, if you want, you can actually right click, there you go, copy and then paste it. If you don't want this, you can delete it and so on. So there you go, click here and you get the same features. Now that distribution plot, by the way, notice it's still there. You can recall it. And there's your probability density function. Oh, StatCrunch calls this density. What is the density here? It's actually incorrect terminology. Usually for discrete distribution, they call them probability mass functions. Density functions are used for continuous distributions. So I'm surprised that Minitab actually uses the terminology density for discrete distribution. The use of words mass or density here, physicists in physics and engineering, these probabilities translate into masses at a given point for discrete. So they call them mass functions. And for the case of continuous, they call them densities because these translate into a region under a curve, which represents the density curve. So anyways, that's what those are. So what do we want to do? Next, I want to actually create I'm going to do that formula mu xpx. So we need to create a column of products. We're going to multiply x times px. So I'm going to go to calc. We're going to go to calculator here. You see that? calculator. And let me actually delete these, because remember I've done these already. That's why they're there. So how do I delete them? I hit delete button and it doesn't do it. That's okay. So here's how we're gonna do this. In yours anyway, these K's, you don't have those actually. Okay, and I really wish I could delete them somehow here, but it's not letting me. Okay, don't worry about these, but you should have X and PX. Okay, so we're gonna actually create a column of XPX, right? So right in here, that's where you label your column. So I'm gonna call that X times probability of X. You see that? Whatever you want to label it. Now the expression is actually the formula, and you don't have to type this. If you hit X, select, there you go, X, and we're going to multiply it. So this is the multiplication symbol, times, we're going to multiply by probability of X, that's in column 2, and there you go. See, that's my mathematical expression. It's XPX, and it's going to create a column, and that's where it's going to place the products. Hit OK, and there you go. You see they appear here in your worksheet. Now let's create actually our next column. We're going to do our deviations now, right? The square deviations. So if you want, we can actually create a column of deviation to really take it step by step. Let's do that. So it's going to look slightly different than what's in my notebook that I showed you. I'm going to go calculator, and this time I'm just going to call this deviation. Okay, delete that one. So what is a deviation? Actually, here, let me go back. Sorry. The reason is this, because in order to do the variance, remember we have to know mu. So let's go ahead and calculate mu, because mu is the sum of XPX. In other words, if you add these up, you get your mu. So I'm going to do that. I'm going to go to, this time, go calc, column statistics. Okay. And here it gives you a list of statistics. So for that column of XPX, and there you go. Let me backspace this one. And there you go. So what I want to do is I want to calculate the sum. What do I want to calculate it for? If you click on input variable, it gives you the list of your variables. So my input variable is going to be what? XPX, right? I want the sum of XPXs. There you go. This is like your sigma. And store the results in optional if you want to. Let's see, where are we going to store it in? Let's store it in, I'm just going to call it mean of X. There you go. Oops, too many items. Let me see, XPX. Oh, I see. Didn't like the mean of. So I'm just going to call it mean hyphen X. The following is a column X. Okay, it didn't like that. So let's just call it mean. And there you go. Now, one thing, by the way, notice it didn't show that mean in here, right? But it's there. That mean is actually there. And now we can actually use that mean in our computation. Okay. So now I'm gonna go to cal. You know what? That's okay. Because I ran this before, so it remembers a whole bunch of stuff I've done already. That's why you see these things are already pre-filled. So let me do this. I'm gonna actually pause this video and close my Minitab and re-invoke it with new data. Okay, so everything, all the fields are clear. Okay, everyone, I'm back. Sorry about that again, because I created all those outputs before, so Minitab was keeping track of my session and all the fields are pre-filled. So what I did is I actually closed Minitab. I didn't save anything. So I'm just going to redo everything again with you. So at this point, you guys are ahead of me, right? You've already done XPX. So let me do that. I'm going to go to calculator. And you see, now it's clean. I don't have all those extra stuff. And I was afraid those will confuse some of you. Okay, so we're going to store the results in variable. I'm going to call that x times px. Okay, so our expression. What is the expression? We're going to multiply x times px. Now, here's the thing, by the way, folks. Let me do this. I'm going to assign as a formula here, okay? To show you what's going to happen here. Whether you check or uncheck this. First, I'm going to check it. Okay. And of course, there you go. Now notice here, there is a green check. Okay. And in this check, it actually shows you, there you go, what that formula is. X times px. Okay. Now, one thing I do, let's say I go in this field and I'm actually want to delete it. So I'm hitting the delete button in the top right corner on my keyboard. And you can kind of see the tweak that you see flashes in C3. It's not allowing me to delete these. Let me go up one. I'm trying to delete this one. It doesn't let me delete it. But let me actually delete the 2 here. You see that? 2 is deleted. Look at this one. 1. I can delete those. But I cannot delete these entries because they are input as formulas. Now, look what happens. 1, 2. Because it actually has a formula in this column, right? In this column, there's a formula. If you need to, let's say you don't want the formula in here and you need to get rid of this column, the way to do it is after you check that is right click. Actually, let me select the column and then right click and you can delete cells. There you go. So the column is free now. So that's what that formula does for you. If you assign as a formula, remember, you cannot delete it. You can delete your data, and when you put new data or edit it, whatever, the formula is recalculated. So let me, there you go. See, it remembers my formula. I'm going to unassign this formula and hit OK. And there you go. Now I have it. Okay, now let's calculate the mean in here. Okay, let's calculate the mean, and for the mean I'm going to go calculator. Oh, actually, let me go column statistics. We're going to calculate the sum. Now, input variable is going to be what? XPX, right? That's the variable we want to add in that column. Now, store results in optional, it says, okay, I'm going to store this in mean dash x. It may not like that because of the x. Yeah, it doesn't like. It says a new variable cannot be used in a through construct mean, a single store. Okay. I'm just going to call it mean. And there you go. So we have now the sum of xpx. Now, one thing is the mean is actually stored now. We can use it now in a minute. So let's do our next column. This column, we're going to do our deviation. So I'm going to go calculator. We're going to call this our deviation column. Okay, so how is the deviation calculated? That's when you do x minus, and look, see the mean is here. It was calculated and now you have access to it. X minus the mean, and hit OK. And there's your deviation. Now we're going to square the deviation. Okay, so in fact I'm going to call it deviation dash squared. Okay, so that'll be, oh, actually let me not do that. I'm going to do that in my formula. So we're going to square the deviation now. So I'm going to go calculator. this, we're going to call it SQ dev, square deviations. And for this one, since we have deviations, there you go, we're going to square them. So shift and 6, that's the hat or the caret sign, that will square it, or raise to a power, and then the second will raise it to the second power, or you can hit this, that's the hat sign. Okay, and there you go. Now you square that, square, you get these numbers. Okay, and finally we're gonna do what we're gonna do square deviation times the probabilities. So in this column, calculator, and this is gonna be and then we're gonna add them, right? So I'm just gonna call this SQ deviation times probability of X. That's the actual formula we're gonna do. And this one, we've done square deviations, right, multiplied by probability of X. There you go, and hit OK. So there you go, we have a square deviation px. If you add these up, that's actually going to be the variance, right, if we sum these up. So I'm going to go calc, column statistics, we're going to sum. And what are we going to sum? When you get rid of what was in that field, input variable, gives you the list of these columns. It will sum any one of these columns, the entries in that column. We want to sum square deviation px, right, and show the results in if you want, you can put it in since these are going to be variances, I'm going to call it variance. Okay, and now we have those. Okay, so let's actually now insert those in here, right? We want to now insert them in our spreadsheet, the numbers that we found. Oh, and also let's calculate the standard deviation. Remember, that's the square root of the variance. Calculator. I'm going to call this now standard deviation. And the standard deviation, that's erase that. Type SQRT, that will take the square root of variance. Close parentheses and hit OK. Now we have our standard deviation, and there you go. You see that? The standard deviation is there. And we're going to put the variance in here and the mean in here also. Okay, so now let's put the variance and the mean in here. So we have our standard deviation. Let's do the variance. So I'm going to go calc. We're going to go to calculator, and right in here I went ahead and typed, you can do that, type var parentheses x close parentheses. This was in there, so here's how I got it in there. Just double click variance. Now check assign as a formula so it appears in your spreadsheet. Actually, if you don't assign as a formula, it's not going to appear there. Hit OK, and there you go. Let's put the mean in there also. So I'm going to go calc. Oh, oops, sorry, not column stats. We're going to go calculator, and I'm going to call this mean of X. Hopefully it will like that. If not, it will adjust it. And I have the mean here, right? There you go, mean, assign as a formula. Okay, and there you go. So these are the numbers that we had. Okay, so this is how this is done. So hopefully you can again rewind and watch this as many times as you like. Alrighty, so let's continue on. We're done with this section, by the way. In our next section, section 2.5, I'm really not going to do much in this section. This is like a whole couple of minutes. We're looking at continuous distribution. Well, the probability distribution of continuous random variables will be continuous. And the idea is that with continuous distributions, we have what we call a smooth curve. So suppose these are the histograms for a continuous variable. Then if you smooth over them, this is the idea of a smooth curve over the histograms. And there you go. What we're looking at the curves actually. We don't care about the bars. Try to remove the bars. So we'll just keep the curves. And of course, with any histogram again, we are interested maybe in the measure of location, the mean, and find the deviation and so on and so forth. So, but in order to find the mean and deviations for these, we need to have knowledge of integral calculus. So we're not going to do anything like that in this course. So we'll look at one well-known distribution, the normal probability distribution, in a minute here. That's the focus of our continuous probability distributions for now. Now, one thing that's important in here, okay, the important thing is that probabilities are areas under the curve. So again, these the probabilities are areas under the curve for any continuous probability distribution. That means if I need to find probabilities, I should be able to find the area under the curve. So keep that in mind as we go through. Now, in chapter 3, we're only doing one section, section 3.1. We're going to talk about probably one of the most important probability distributions that we could come across, and that would be the normal distribution. Some of you have probably seen this distribution, but I'm going to look at it closer and work with it somehow. So there you go. And this is what a normal distribution looks like. Notice the distribution is continuous in that there are no breaks, holes, jumps, or gaps in this curve. So that's the idea of continuity. Okay. Now, this is what they call a bell-shaped distribution, and actually the three-dimensional version of this distribution, I'm not sure if some of you may have seen it, but the three-dimensional version of this distribution indeed does look like kind of like a bell. And let me try to draw one for you here. And there you go. This is kind of the three-dimensional version of it. Okay, so there you have it. That's behind the scene kind of thing. So that's what the three-dimensional version of a normal distribution is. It's normal in all directions. Okay, now this normal distribution has mean. Center of the distribution is mean mu. Its standard deviation is sigma. Okay, now something interesting about the location of a standard deviation in a normal distribution is that I've done kind of a blow up of that segment of the curve, let's say, which you will see over here in a moment. It's right about here. That's this point right in here is over here. Okay, and this location of a standard deviation actually is a very interesting point on the curve. If you look at the curvature, or some call it the concavity, the measure of bending of a curve, the concavity of this curve is downward. The green arrows point downside, so they're downward. The blue arrows point upward, so you have downward green, upward blue. And at some point, as you move, let's say from the lower part, and you come gradually, you work your way higher. So as you come in this direction, notice the up arrows, and if you go down from the other direction, at some point the green and blue are going to come together. The point where the concavity actually changes from up to down or from down to up, it's called the point of inflection. Well, that point of inflection happens exactly at sigma, standard deviation, one deviation away from the mean on either side. So there's another point of inflection on this side. And those points of inflections occur again exactly as the one standard deviation away. Just something interesting. We can actually locate those, and usually we do. Now, we're going to look at some of the properties of this normal distribution. First, the way we're going to label this distribution, N stands for normal, And then we put what we call the parameters of the distribution in here. The parameters of the normal distribution are the mean and deviation, sigma. Now, the domain of the random variable x, whose distribution is normal, is negative infinity to infinity. That means all real numbers. So x could be any real number. That's what makes this so useful. The total area under the curve, if you look at the area from negative infinity to positive infinity, all of this area under the curve adds up to 1. Now again, I cannot show you that because in order to show this, we need to look at the form of the function, and then we go through integral calculus to do it. So that's not necessary for our course. The distribution is symmetric about the center where the mu is. And by the way, the center, the peak of a distribution is where the modal value is. So mu is not only the mean, it's also the mode of this distribution, the peak of the distribution. And the median is also the same. That means 50% of the scores are above, 50% of the scores are below this. So for the normal distribution, mean, median, and mode are all the same. Mode is the most frequent score, and that's mu in this case. 50% of the area is above, 50% is below the mean. So mean, that makes mean actually the median. That's the characteristic of the median. The distribution is asymptotic. That means, by that, what do we mean asymptotic? That means the tails of the distribution, although they look like they're touching, but they really do not. If you do like enlarge that area, it doesn't. But it's hard to see it on the graph. So they get very close to the x-axis. They go right alongside of it in both directions indefinitely without touching nor crossing it. Okay, and I already mentioned the parameters of distribution are mu and sigma. That means I need to know the mean, I need to know the deviation. Minitab needs to know the mean, and Minitab needs to know the deviation so it can graph it. And there you go. So here are some graphs of these. Okay, now over here, you're looking at 3 different normal distributions. Okay. And for these normal distributions, they each have different mean and different deviations. So the center of this distribution, the green, is at -2. The center of this one is at 3. The center of this one is at 9. The deviation, sigma, of this distribution is 1. Deviation of this one, 1/2. Deviation of this one, 2. This is the largest deviation among the 3. This is the smallest. The larger the deviation, the more flat, pancake-like this distribution is. The smaller the deviation, the higher the peak, the more narrow the distribution gets. We actually like this because we like low deviations, relatively speaking. And this is what deviation 1 looks like. So we're looking at 3 different normal distributions. There are infinitely many normal distributions. Just change the mean, change the deviation, and you get a different normal distribution. Now, to the right, you actually see a glimpse of what Minitab can do. Again, I'll show you how to graph these in a minute. We do lots of these in a minute. So this is the normal distribution plot in Minitab. I actually have 2 of them. There you go. This one, the dotted one, is the one with mean 5, deviation 2. So the center is right in here. The center is at 5. And deviation 2, so this is the inflection point is. This one, the center is at 0 deviation, see mean 0 deviation 1 is this one. That's your standard normal. Okay, so there you have it. Now, if the mean of the normal distribution is 0 and deviation 1, it has to be exactly those 2 numbers, exactly the same. Then these normal distributions are commonly referred to as standard normal distributions. Okay, that's what these are. Standard normal distribution. The word standard here means just that. This distribution is kind of the standard for all other normal distributions. So that's what these are. Now, a random variable that follows a normal 0, 1 is called a z-score, or simply a z-variate. Variate or variable. Z-variate. That's what it's called. Okay. And this is what the 0, 1 distribution looks like. Standard normal distribution looks like that. Okay, now again, Minitab uses, see in here, it calls the variable x right down here. That's what Minitab calls it, x. Forget that one. There you go. We actually call this z. But again, Minitab uses x for everything, for all the variables are x. And they don't need to change it every time. Okay. And there you have that one. So that's what it looks like. Now, let's actually try these. And we're going to go to Minitab, and we're going to try to do this in Minitab now. Okay. So what I'm going to do is I would like to find these probabilities. Okay. Probability, and this is actually what the z is. So in part A, since the distribution is here, I can actually do this. Probability of z greater than or equal to 2 means this. This is where 2 is, right? And this shaded region, this area to the right, that's what I want to know. What is probability of getting a z-score greater than or equal to 2? And in case of part C, for example, probability of between, what you call it, between 1 and 2.4. This is, say, 2.4, and 1 would be this. This is what we want to find out. We get better graphs of these in a minute. But I just want to show you what we do usually is we translate these probability statements into areas under the normal distribution. Okay, and then we find the probabilities. Now, probability of z equal to 2. Okay, I'm actually looking at part B now. Okay, so in part B, this probability, I'll show you this in StatCrunch how it becomes 0. I'm sorry, not in StatCrunch, sorry, I'm thinking of another software. In Minitab, I'll show you how this will be 0. But in general, I want to generalize this. This is a true statement about any continuous probability distribution, not just normal, is that probability of exact values of the random variable is 0. And the reason is true because remember, probabilities are areas under the curve, right? So if I look at, for instance, let's say here's where 2 is, exactly 2. If I want to actually find probability of the area under at 2, I should find area of a line. And a line does not have an area. So it's for that reason, because this line doesn't have an area. So that area will be 0, which means probability of that is 0, which is kind of ironic too, because let's say, for example, the assumption is that, for instance, the cholesterol level of people follows a normal distribution. So if that is indeed the case, let's say I want to know what is probability the average cholesterol is going to be, I don't know, 180. Well, according to this, the probability of getting an average of 180, or even an individual score to be exactly 180, is 0. And that has to do again with the measure theory and the theory of measurements and things like that. So, but keep that in mind for our work. So one thing, the immediate consequence for us folks is this. See, in part C, I have z greater than, right in here, I have z greater than 1. For this one, whether you put equal sign here or not makes absolutely no difference. In part D, if you look at part D here, z less than negative 1.96, Whether you put equal or not makes absolutely no difference in this one. Let's see that. So that's what the implication is. Whether you include, exclude makes no difference. So let's see. Any non-standard normal distribution can be standardized. Oh, before we actually do that, let's actually go now to Minitab and try to do these. Okay. So I'm going to the Minitab next. And here's Minitab. We still have the previous run up here. Okay, now in order to work with normal distribution, we're going to go to this graph tab. See, when you click on graph, you get a whole bunch of good stuff in here. We want to go to probability distribution plot. Okay, and there you go. Now there are several options in here. View single actually will graph a single distribution for you. So let's say, how did I do my standard normal 0, 1? I went here actually and clicked. It's already default is that. I just hit OK. And it says, okay, well, what distribution do you want me to graph? We're doing normal, so I'm going to keep that as normal. Mean 0, deviation 1. There you go. That's the standard normal. Okay. And there is the graph right in here. And you can scale this graph if you like to. Yeah, the size of the graph, you can change it. Right in here, you can save the graph, by the way. Let me go edit the graph. And to resize it, that's not where I do this. Let me try this one. Yeah, edit graphs. And let's see. Here's edit graph options. Oh, it's not working. Okay. Anyway, you can mess around with this and see. But if you just left click on it once, select it, and right click, again, you can send this to the Word, or you can copy the graph. And if you like, you can save it to a file. You can delete it if you don't like it. Okay. So anyway, this is how you graph them. Now, let's find those probabilities, shall we? So I'm going to go to graph and then probability distribution. And this time I'm going to go to, if you want to, let's draw two distributions. There we go. Go to two distributions. And both of them, you can have a binomial, normal, whatever. I'm going to keep both of these as normal. Let's say we want to do a mean 0, deviation 1, and then mean 0, same center. And this time the deviation, let's make the deviation, I don't know, 5. There you go, 5. And this gives you options on what you want to do. I'm going to actually overlay one on top of the other. And there you go. So this is what you get. Okay, and this is the overlaid graph. Okay, this one. All right, and now let's do those probabilities. So I'm going to go to graph, probability distributions. Now, this time, I'm going to go to view probabilities. This is where you actually, later on, this is where you find probabilities for the normal distribution. Hit OK. Now, first you need to define the distribution. Again, you can do this for any distribution. Our focus is on normal. Now, my example was standard normal because I use z-scores. So that means mean is 0, deviation 1. You can type those in. Now, don't hit OK yet. Go to shaded area. See, this is how you introduce the distribution. Now, here's your shaded area. Okay. Now, for shaded area, you're going look at the x value, and these are the various formations under the distribution. If you want to find the area to the right, that means greater than. Area to the left, that would be less than. Both tails, we'll look at these when we do confidence intervals. And if you want between two numbers, you go middle of two numbers. So the one I wanted to do was greater than. That means right tail. The x value, which is really the z-score, was 2. Hit OK. And there you go. So the answer to that exercise, that problem, probability of a z greater than 2 is going to be 0.02275. Okay, I'll copy these down to transfer these to my notebook in a minute. And next one was probability of a z between 1 and 2.4. Okay, so I'm gonna go again to graph, probability distribution plot, probability. Okay, we are doing between two numbers now, right? So shaded area, middle. There you go. Between the lower number was 1, the higher number was 2.4. Hit OK. And there you go. It shades the region that corresponds to that statement. And that number, the probability or the area is 1505, 0.1505, means a little over 15%. Probability of a z less than negative 1.6. Graph less than, so that means my shaded area is to the left. Less than the value, negative 1.96. And hit OK. And this one is 0.025. Okay, notice how nicely it shades the region and it gives you the probability. The 0.025 is right here. Now, let me show you that probability of z equal to 0. This is how you get StatCrunch to verify that. I go probability between. Okay, now shaded area. Let me go x value middle. Okay, so for 2, I'm going to put the lower number 2 and the upper number 2. Between 2 and 2 means exactly 2, right? Look at that. Boom. There you go. You see that 0 in here? Because the area of a line is 0. A line does not have an area. It has length, but no width. So that's 0. That probability is 0. Okay, so I can now transform these onto my notebook. We can actually write the answers here for this. So probability of z greater than or equal to 2, that one turned out to be 0.02275. 0.2275. Probability between 1 and 2.4 was 0.1505. And probability less than negative 1.6 was 0.025. And there you have it. Okay, so pretty easy if you know where to go and get those numbers. Now, something that's in your book, in every statistics textbook, is that if we have a non-standard normal distribution, we can actually standardize it to where it turns into a mean zero deviation, one normal distribution through this transformation right in here. And that's how you create the z-scores. So we use this in future chapters, then I'll tell you more about it. But for now, we don't need it. Now, let's take a look at actually something different now. Okay, so what we want to do now is, given the random variable x follows a normal distribution, with a mean of 100, deviation 5. Remember, first number is mu, second number is sigma. And this symbol, the tilde symbol here, means follows. Okay, so random variable x follows normal with those parameters. We want to actually find these probabilities. Okay, so we're going to do these again from Minitab, right? You're going to go to Minitab and try to figure these out. Now, I have already done these. So these are the answers actually, but we'll go together and actually verify these numbers. But there you go. Those are the answers. Okay, so let's see how I got these answers, and you can verify them later too. So I'm going to go back to Minitab again, and we go graph, probability distribution, and let's say we want to view probabilities. Okay. This time, what I've done is actually change the mean, right? I no longer have a standard normal distribution. So the mean is now 100. So I type 100 and deviation is 5. Now don't hit OK. If you hit OK, you'll just draw the distribution. Now let's go to shaded area. And what do we want to do? The first probability was greater than or equal 104. Greater than or equal means right tail. The value was 104. There you go. Hit OK. And that's how I got that number. You'll see that in my notebook. Probability less than 89. You go graph, distribution. Again, view probabilities. This time shaded area is going to be to the left, less than. The score is 89, hit OK. And you get this number, 0.0139. And finally, between 93 and 107, so I'm going to go graph and view probabilities, and this time shaded area is in the middle somewhere. Middle of 93. And the higher the upper number is 107. Hit OK. And there we have this one. So the probability is 83.85. So that's how I got those numbers. Let's go there, and you see that's how I got these numbers. All right. So hopefully now you're comfortable working with normal distribution and finding probabilities in any formation. Now, here's another example I made up. This time, what's different is that we just got out of example where you were given the z-score, the x-score, whatever they might be, and you were asked to find the area. In here, you're given the area, you want to find the z-scores. It's just the opposite of what we did. So let's try working some of these problems now. Okay. So we're going to do probability of z less than. Now, here's z less than z. This is the random variable. The one in boldface is a value of that random variable. Random variable, a value of it. Random variable, and the value of it. So in part A, I want to find the z-score. See the value of a z. I want to find the z-score so that the area to the left of that is 5%. Tiny area to the left of z-score. Okay, 0.05, and that's z-score is what we want to find. So now I'm going to go to, and remember these numbers so I don't go back and forth. I mean, I write them down I have them on a piece of paper, right? And we have 0.78 and 0.05 less than, 0.05 greater than. Okay, so I'm going to go again to, by the way, look at the navigator. You see all of these? If you don't want these, you can right click and delete on any one of them that you want. If you, let's see, there you go. Usually shift or control does it, but it's not responding to shift or control to select more than one. Yeah, it doesn't let me select more than one. So I'm just deleting all of these stuff, so it's not causing too much clutter. Okay, now let's do the ones that I just showed you. I'll go graph, probability distribution plot, and we're going to go back to view probability. Now here's what's different. We're back to mean 0, deviation 1, right? Because we're looking at z-scores. Now shaded area. Now this time, see x value is selected. Go ahead and check probability. We actually now gonna assign probability, and Minitab will give us the z-scores now. So the first example, we want a z so that the area to the left is 0.5. So left tail, probability 0.5, will keep that default. And there you go. The score, the z-score is negative 1.645, right? So I'm going to write that and then write it into the notebook in a minute. Probability of a z greater than a z-score, we want that to be 0.78. So I'm going to go graph, distribution plot, view probability, shaded area, probability. Now greater than means right tail. Right tail, we want it to be 0.78. Hit OK, and there you go. Negative 0.7722. That's what that z-score is. And this is the z-score. And finally, we want a z-score, so the area to the right is 0.5. So I go graph, plot, and to the right of that, shaded area, probability to the right is 0.05, which is going to be positive 1.96, right? Remember, for the negative 0.05 on the left was negative 1.645. Now it's 1.645 positive. Okay, that's what those are. And let me just make up one that you see the symmetry of the distribution here. View probability, and this time we want in the two tails, both tails, probability to be 0.5 in each. That means I'm going to change this to 0.1. So what happens is that 10% is going to be split between two tails. So I'm going to get 5% on the right, 5% on the left. You see that? I'm holding the mouse over that normal distribution, and it reads shades. Hold on. Shade area. Where did it go? There you go. Shade areas under the distribution curve with equal tail probability p over 2. And there you go. See the symmetry of that distribution? 0.5 on the left, 0.5 on the right, 0 in the center, and these are symmetrical values. Okay, and we're done with that work, so we can actually put the answers back on here now for this one, right? So the answer to the first part was negative 1.645. Here, z is negative 1.645. This one, we got the z-score to be negative 0.7722. And for this one, the z was, by symmetry, 1.645. And there you have it. Exactly what we did. I just ran it earlier. We're almost done, folks. I know you're getting probably tired of this, right? Okay, now check out the empirical rule here. This is the word empirical here means based on actual data. So empirical rule says that for any mount shape or nearly normal distribution, now the authors of your book actually use the normal distribution, but for any distribution that is nearly normal, about 68% of scores of the measurements of the values lie within one standard deviation. Okay, so this is mu plus 1 sigma. And this one is mu minus 1 sigma. In that shaded region, there lies 68% probability, or 68% of the scores lie in there. Within 2 deviation, that's 2 deviations above and 2 deviations below, right? In this interval, in that interval, there lies 95% of scores, and 3 standard deviation, that's 3 to the right and 3 to the left. Notice how the distribution has tailed off in both directions. So that's 6 sigma total. 3 sigma above, 3 sigma below. And that covers almost all the scores. 99.7 score of the measurements are there. Okay. So there you go. That's what the empirical rule says. And let's take a look at an exercise here. And then I believe we're going to be done with this. Yes, we're almost done, folks. So let's take a look at this application, if you will, from your textbook, exercise number 8. In this exercise, the question reads, the capital asset pricing model, CAPM, is a financial model that assumes returns on a portfolio are normally distributed. Suppose a portfolio has an average annual rate or a return of 14.7%, that is the average gain of 14.7. So that's mu. With a standard deviation of 33%. That's sigma. A return of 0, of course, means the value portfolio doesn't change. And negative means it loses money. And a positive means just that, a positive return, a gain. In part A, what percent of years does this portfolio lose money? Okay, so we want to find the word percent here means probability for us. Okay, that means it has a return that is less than 0. So less than 0 means probability of x less than 0. So that's what we want to find, right? In part A, there you go. In part A, we want to find probability of x less than or equal to 0. And in part B, it reads, what is the cutoff for the highest 15% of annual returns with this portfolio? So here's a case where actually in part B, we are given the highest 15%. This is an area, right, under the curve. So we want to find probability of x greater than, this is random variable x, greater than some value of x that we want to find, so that's 0.15. See, so we were given the area to the tail, we want to find the cutoff point. Okay, so we're just going to go to the normal distribution, right? Now remember, we're going to a normal distribution with these parameters for this exercise. In this exercise, mu is 14.7 and sigma, standard deviation, is 33. And we know these are all percentages, right? Now you got to be careful because this is a percent and that is a percent, but there are two different ideas. This is not, the 33% is not a probability, it's actually a value, whereas this 15% is a probability. Okay, so let's go and finish this off. I'm gonna go to there you go, Minitab. So I'm gonna go graph, distribution plot, and we want probability of x less than 0, right? So that means we want view probabilities. We don't have mean 0, deviation 1, right? Remember the mean was 14.7. Okay, so I'm just going to type 14.7. Deviation was 33, which is rather high relative to the mean, but that's okay for this one. Shaded area, so we want less than, that means left tail. And we have an x value for it, left tail. The x value we want to know less than 0. And there you go. Here's the answer. The answer is 0.328. 0.328 is what that is. Now, for the last part of that exercise, we go graph, distribution plot, view probability, okay. Same parameters of the normal distribution, same mean, same deviation. We're just going to change our, let's see, shaded area. This time you want greater than means right, and there you go. Change x that x to probability. See, we're going to give it a probability of 0.15, and that'll find the x cutoff point for us. And again, we want greater than, so that's got to be right tail, right? Make sure that the right tail is selected. And it's 48.9. That's where the cutoff is. 48.9%, that is. Okay. And with that, let me show you. This is what I got. So the cutoff for the highest 15%, these are the highest 15%, is 48.9 annual return. And the probability that they lose money, right, less than, losing money, less than 0 is better than 32%, almost 33%. Okay, folks, thank you for your patience. We covered a lot of grounds here, and my notebook here can't take it anymore, right? So it's going to come alive in a moment. It's running in the background. So anyway, this will complete our exercise that we did. And we are done with this lecture, folks. So we're done with week 2, and there you go. Let's come back to life. We've lost it again. There you go. It's back again. So please, if you have any concern, review this video. I know, again, I apologize for being it so long, but just watch it a little piece at a time every day, and that makes it better. Okay, and hopefully you're okay on this video. And we're done with the lecture for week 2 of instructions with this.